All right, so let's go ahead and review for the exam, or for the Chapter 3 test here. Chapter 3 in the book we're in right now. But anyways, linear regression and prepping for things. So in terms of, if this were the graph, kind of get back to that whole Old Faithful. I think I've used this data set or similar data sets in the past, where the duration of the actual eruption of Old Faithful. Remember, Old Faithful is a geyser. And we're looking at as my explanatory variable duration. How long did it go off for? And then how much time in between to use as a prediction. All right, so that's what I have going on here. So duration time of the previous eruption is my explanatory variable, and the time until the next eruption is my response variable. So what do I say? I describe this graph. So again, you're thinking form, direction, strength, and outliers. Okay, so here for outliers, I would say that all data appears to follow the pattern. There's nothing that's out of the ordinary. There do not appear to be any outliers. I would write all that down. All right, direction. In this case, it's positive association. A positive association, which means as duration increases, time in between also increases. So that's my direction. Positive association, which means, included which means, as the duration of the eruption gets longer, the time in between also gets longer. Form, this appears to be linear. And strength, I would say this is fairly strong. I say it's fairly strong because you look, all the data is pretty consistent in what's going on here. Yeah, it might be spread out this way a little bit, but it's all following that linear pattern. All right, so if I wanted to do just a single statement instead of doing the listing of things, I would say there appears to be a strong positive linear relationship, which means as duration increases, so does the time between. All data follows, with all data following that pattern, leaving no potential outliers. Boom, if you don't, didn't get that down, pause, rewind, go back and listen to it again. And then I'm told, now R came from that last graph where they said R was 0.877. And then I need to find the least squared regression line. Now, we were given other tools in the past for finding the least squared regression line, but this one's a little bit different in terms of what are we going to use and how are we going to figure it out. Because I'm not given the constant, I'm not given the coefficients, I'm not given the slope, but I'm given a whole bunch of pieces of information between duration times, which was my x, and my time in between eruptions, and that's my y. All right. So if I go to this, this is taken from the formula card. These are all the formulas that we have about linear regression. And I start looking at this and go, okay, well first I'm going to write the equation y hat equals b naught plus b1x. Let's start looking to see what do we have. B naught, or the y-intercept, says, well, if I have those three things, the average of the y's, the b1, and the x bar, I can find this value here. Well, if I go back just to that previous screen, which you can go back and look at, we know x bar and y bar because those were the averages of the x and the y variables. And I encourage you / challenge you, really / you need to go do it. Just go do it. Go back a little bit and look to see where these two values came from. This came from the x side, and this came from the y side for the x bar, y bar. But I'm not given b1. Well, then I look and I say, oh, well, wait. I've got this formula as well. b1 equals r times standard deviation of y over standard deviation of x. R was given in that last one as 0.877. And I also know, if I go back to that previous slide as well, that I'm given both of these numbers, which I'm just going to go ahead and grab now and bring over here so that way we can look at it some more. So the standard deviation of y, remember this was my x, this was my y, so the standard deviation of y is right here. And the standard deviation of x is right there. And some of you might be saying to yourself, why does it say x over here and x over there? Well, because I did one var stats for each of them. I didn't say, hey, do this one and call it variable x, and do this one here, call it variable y. They were given differently. But anyways, if I take that, I can plug them into this equation, the y and the x, and then the r in there to find b1. And when I do it, I get 10.356. So that's my b1. And then I can plug that value into this equation for b1, along with this number for x bar, and this number here for y bar. Pardon my arrows there. Alright, and the reason why those go in there is that the least squared regression line, remember, least squared regression line goes through the data point, the average of all the x values and the average of all the y values, which is why it's x bar and y bar. And then I plug this in, and I get that my b naught equals 33.98. So again, took the y hat value, put that in there, 77, I'm going to subtract, so I know it's going to be less than 71. Subtract b1, which was 10, times the x bar, 3.576, giving me this number as b naught. So now I have my equation up here. Right here, I have this equation. I'm just going to plug in numbers. Y hat equals b naught, which we said is 33.98, plus b1, which we calculated down here, 10.356x. There's my least squared regression line. Y hat equals 33.98 plus 10.356, x. So that's how I'd find the least squared regression line from this type of computer output. In this case, it's a calculator output. Then I could go along and say, yeah, if I happen to know that an eruption lasted 4.5 minutes, what's the estimated wait time until the next eruption? Well, here, let me go to the next slide. So I said if we happen to witness an eruption, so because that's what you do when you go to Old Faithful, right? You get your stopwatch out and you see how long it takes, and we find out that it took 4.5 minutes from the beginning of the eruption to the end of the eruption. How long do I think I need to wait until the next eruption? Well, which was the x and which was the y? In this case, the explanatory variable was eruption time, and the response variable was time in between. So, take this and plug it in for x. Y hat equals 33.98 plus 10.356 times 4.5 for minutes, and I get that I expect it will be approximately 80.52 or 582 minutes until the next eruption happens. That's my predicted time. Then what I can do is I can actually measure that time, start my stopwatch again, go do something, come back, because to sit there for 80 minutes you might be waiting a while, over an hour. But you can actually time it all out and then find out how long it actually was, and then find the residual, which is awesome. Alright, so that is pretty good review in terms of looking at things that are going to happen on this test. Let's see, just little nuggets of information. What if a residual plot shows a pattern? What does that mean? It means that the linear model is not the best model. Okay. Can you figure out outliers based on looking at a residual plot? Yes, you can. So if you look at the residuals and there's one data point whose residual is just really crazy compared to all the others, probably an outlier. Can you determine the shape of a distribution based on the residual plot? Sort of. but not as easily as other techniques that we'll use. What if we remove an outlier from a data set? You know, if I have data here like this, and then I have this one wacky point down here. All right, so the original line goes through like this. What happens if I remove this point right here? Well, since right now that point is pulling the line towards itself, my new line is going to have a different slope, bouncing or moving away from that influential data point. All right. So that means the slope will get a little less negative. The y-intercept will get slightly lower because it'll still hinge on whatever that x bar, y bar value is. Remember, because it goes through, you know, whatever that data point is here and here. That particular data point is x bar, comma, y bar. Let's see, those are basically it. So my R value on that last one was 0.877, which means, so this is kind of going back to the other thing, so you know, for this, kind of ignore this for right now. That means 76.9% of the variation in time in between eruptions, using this linear model, is linked back and attributed to the variability that we see in the times, and that would be an interpretation of the R squared. All right, so 76.9% of the variability that we see through this linear model in the time in between eruptions is linked back to the length of the eruption itself. A couple different ways of saying the exact same thing. The percent variability in Y as compared to the variability in X using this linear model. That's enough for now. I'm talking too much. Don't freak out. Know your terms. Practice problems. Be familiar with your note card. And I will see you when you get to class.